So let x and y be i.i.d. continuous random variables with the PDF being f, mean u, and the variance sigma squared. We know that the expected squared distance of x from its mean is the squared sigma, so it's basically the variance, and the same goes for y. The problem here is about the expected squared distance. We're going to calculate this distance in 3 different ways. Well, basically in 2 different ways. The first one is just asking us to write down this expression in terms of a double integral. So let's start doing that. So the expectation of x minus y squared is, and here we're going to use the 2D lotus, is the integral, or it's the double integral over y space and x space of x minus y, so all their realizations over that support of the joint distribution of x and y, dy dx. That is the integral. Now, this joint, because of i.i.d., simplifies to f of x, f of y. Alright, so that was pretty straightforward, just using the definition of the 2D lotus and the definition of expectation. So now, in the second part, we are asked to expand the squared and evaluate the double integral and show that that corresponds to 2 sigma squared. Okay, let's do so. I'm going to start by copying this little thing we have here, duplicate it, move it here. I'm going to write this using the i.i.d. We just calculate it. Now we expand xy squared to be x squared minus 2xy plus y squared, like so. And we have the double integral over f of x, f y, dy dx. All good. Now we're going to just rearrange all these terms and see if we can get something like resembling the variance of x and y. Why the variance? Well, basically because we want to show the right hand side, and that is indeed 2 times the variance. So let's see if we can get it into that shape. So over x and y here, so let's do f of x, f of y, x2, and that's f of x, f of y, and dy dx. Well, the same thing here, f of x, oops, f of y, and minus 2xy, f of x, f of y, dy. Oops, there's a lot of terms here. Dy dx. Just going to move this tiny bit to the right to make some space here, like that. And we have the plus f of x, whoops, integral over x and y, y squared dx dy. All right, so what does this say here? Well, basically we can see in this term here and that term here is that we are integrating over y and x. We don't have an x here, and I just realized I made a mistake here. I forgot to add the densities fx, fy. It's critical, obviously. So what is happening here is that we are integrating over f of y, sorry, over the integral of y over the whole density of the whole support of y, but that will just be 1, right? So this integration disappears, and the same follows from the x term here. So what we end up with is basically f of x, x2, f of x, dx, right? Because the term, as I just said, disappears in that integration, and the same thing will hold for the y term, but then here we have f of y, right? But now it's the x that disappears. So f of x, so we have f of x disappeared, we have y left, y2, f of y, dy. All right, so what do we have in the middle term? Well, here, this 2 obviously goes, we could take that out, is that we have the terms being the expectation, right? So we have f of x over x fx and f of y dy being the mean of y. But both those terms have mean mu. Okay, so that whole thing here becomes just negative, so minus 2 mu squared. All right, so this looks starting to look good, although we have this little term here that looks a little annoying. But what we can do is that we have 2 of these, and this is exactly what we need to show that. I'm going to duplicate this another row here. This we're going to duplicate. Well, actually, I'm not going to duplicate it. I'm just going to show you that that term here, that term there, is the expectation. This term here is the expectation of squared x, right? And this term here is the expectation of y squared. Well, fine. And then we can split up. And what we need to get the variance, we can split up this guy here. We take one of them mu squared. Add there. We can attach the other one here. And then we know that that mu squared is basically, so I'm just going to write this out, squared to mu squared is the same thing as the expectation of x squared plus the expectation of y squared minus expectation of squared. Okay, and this whole thing came from the fact that both y and x have the same expectation and the same variance, and this is in fact the same variance is what we're going to use next, which is now that this whole thing is squared. Whoops. And this whole thing here is squared. That's squared, that squared. And so the result is indeed 2, sigma, sorry. It's going a little too fast here. Sigma squared, which is the variance. And now we have shown that this whole thing adds up to 2 squared. 2 variance. 2 sigma squared, sorry. Too many things going on here simultaneously in my mind. Alright, that's good. Now, in the last part, we are asked to give an alternative proof of results from B. And here we're going to use a trick of adding and subtracting mu. And then just expand this whole thing. Alright, so let's just do that. See where will that take us. Well, it looks like, you know, after we do this expanding, is that we can just basically take the expectation over the left hand side and the right hand side, and then see if we can fiddle around a little bit with the terms to end up with what we want to show. Alright, so let's just write it out. We have the expectation over the distance of the difference between the square difference between the 2 random variables. Now we're going to add and subtract. Well, I'll just skip this part. Basically, this is what we have here in the middle. I'm going to use this result immediately. Write it down. Just to move a little faster. Well, we do want the expectation here, so I'm going to leave this here, and then we have x minus. Let's see, x minus sigma squared minus 2 x minus mu times y minus mu plus y minus mu squared, and then that's the whole expectation over it. Now what we can do is that we just use linearity. And for that, I'm just going to copy this whole thing, duplicate it, write it out like this. Okay. Another expectation here. And another expectation there. Alright, so this indeed here is the variance, right? This is the variance of just another way of writing it out. That's a usual way actually to write it out, of x, and this thing here is the variance of y, and that's also sigma squared. But what is going on with the German side here? Well, because these x and the y's are independent, we can basically just use the fact that you have 2 expectations here. It's basically linearity multiplied, and this only works when x and y are independent. Another way to see that this and this will go to 0 is that we can just multiply out this whole thing and see how the terms cancel out. Just going to use the fact of independence. We have 2 expectation x minus sigma, the same thing here, y minus sigma. Okay, that's good. Now this looks a little tricky. Does this become really 0? Well, this little thing in here is the expectation of x, right? And then we have the other term here. I'm just going to write in parentheses. This will be easier to see. So basically we use linearity over this little term here. So we take in the expectation over x, and the sigma is just a constant. We have expectation of x minus expectation of x, and that is 0. So we end up with 2 sigma squared, which is what we were asked to show.